Well, welcome everybody. We're going to have a quick flyby at looking at some city energy and environment modelling, which we've been doing partly from an academic base, but particularly with a practical commercial point of view, working with our friends at the Energy Savings Trust, and we have this major project together. Now, the thing about cities is that about in the richer parts of the world, about 80% of people live in cities, what we call cities. And in China and India, in China alone, maybe 300 million people are going to move into cities over the next 20, 30 years. And so this is where people are going to spend most of their lives, consuming energy services and living within urban environments. And so we've been developing city energy and environment modelling and databases to try and look at the policies that you can apply in cities. And so what we'll show you today is the sort of academic, the algorithms and so on that we've been developing at UCL, but some of the data and the commercialisation of the model, because we're interested in aiding implementation ultimately, is being done with Energy Savings Trusts. All the data and results I'll show you today are illustrative, because it's with model development, but I think the results are will be reasonably close to what will come out once we've fully developed the databases and the algorithms. And we'll be looking at cities both in their spatial aspects, but also in the temporal aspects and how things will change across the years and indeed across the hours of the day. So 3 years ago, UCL and the Energy Saving Trust wrote a proposal for a feasibility study for this model to Innovate, or a technology strategy board as it then was, and we then secured this 2-year Innovate funded project together, and the working name is SciSIT, Stakeholder City Energy Demand Simulator, but we will be thinking of a sexier title to that, I think, in the end, because it could be pronounced SICETS, which isn't nice. And the purpose really is to help urban stakeholders implement plans. It's not a theoretical academic study, the idea is to help them do things. And so we came up with this scheme where we have a city energy planning forum with these stakeholders, citizens, local government, central, health, social services, NGOs, local industry, energy suppliers and others like finance and so forth. And the idea is that we would design a tool, a data and modelling tool, which these stakeholders can use live in forums to develop plans for technical basis and economic basis and environmental basis to reach these kind of aims: lower fuel poverty, improved health, enhanced energy security and improved economics. And so the development process for this was first of all to do a survey of stakeholder needs in different cities. So consultants from the Energy Saving Trust went out and actually asked different city authorities, what are you interested in? And the result of that process was identifying these primary concerns by city stakeholders. The second phase is to develop the data and model, which is the phase we're in at the moment. And then lastly, the idea is to commercialise this model and apply it to cities. And our first cities are Birmingham and Exeter, and we discuss with them all the time about what they'd like and different aspects of the data and modelling system. I should say, please shout any questions or rubbish or good, bad, whatever you like, as we go through. So this is a kind of overall model flow. We start in our base year with people, households, businesses in a city. And then we come up with scenarios for the stationary sector, efficiencies, and energy supply shares. For non-transport demand, which is mainly buildings, but not only buildings, things like telephone masts and so forth also included. Then we have a transport scenario. We look at different modes of transport and different technologies for transport. Put that into a transport model. And these two together, the stationary and transport sectors, we come up with spatio-temporal energy demands for heat, electricity and gas. This then feeds into our supply models, and we have three where we're looking at the networks and the energy supply for district heating, electricity and gas. For electricity and gas, we're not actually looking at the generation of, say, biogas in the city, but for electricity we're including generation from combined heat and power in the city, and we have a quite separate district heating model. But for all three of these, we are calculating the network costs in the city for the pipes and cables, which are a very, very large fraction of the total capital value of national and city energy systems. From these, we calculate energy service costs. There's a separate fuel poverty calculation, and we get sector totals for energy emissions, costs and fuel poverty. And then our final step, in some ways the most complex one, is trying to estimate air pollution concentrations and health impacts, which, as you all know, are quite high profile at the moment. Now, cities, a sustainable city is actually an oxymoron. Cities import almost all their energy, wherever you are in the world. The idea of a sustainable city is just, in energy terms, is not feasible. They import energy and other resources. And so we have to have a national scenario context of fuel costs and the electricity and hydrogen costs and the carbon contents of the national energy supply in order to work out what the emissions implications are of our energy use in the city, and indeed, if we're generating electricity, say, from combined heat and power, what the value of that is outside. So we have these scenarios, which are loosely based on a number of other scenarios.
So one of the biggest piece of work that I've done in this project is to do with deriving demand from non-domestic buildings, which is one of the slightly more complex sides of it, partly because of the data that's available. So I looked at a few different ways, possible ways of doing it, and basically ended up using a database called OS Address Space, which in theory has the classification of every non-domestic building or business in the UK, and you can link that to the OS Master Map database and then actually figure out the floor area. So I basically used that to derive the sort of approximate floor area for every single non-domestic business in the UK. So, and this costs money, unfortunately, and even though it's a commercial project, our original aim was to use free data. I did look pretty seriously at OpenStreetMap, but this image, basically the underlying stuff is master map, and this kind of shows what OpenStreetMap covers within that. So this is an example area, and you're looking at like maybe 50%. So even though you have to pay for this data, it's much better. But it's not the final answer, because attributing the business types to actual polygons is not a very simple thing. So in order to convert that sort of derived floor area into energy, again, there's not a lot of data. But basically what is available is the display energy certificate data, which fortunately we have a lot of access to and work on in the department. And so I worked on attributing that to the archetypes that I use in deriving floor area. And then you can just simply multiply the data, which is in energy intensities for either heat or electricity, and get an approximate value for electricity or gas demand. And it comes out pretty good with gas, which shows the floor area at least is derived quite well. It's more difficult actually to derive electricity demand, and that's partly because it's slightly less related to floor area, so you've got quite different types of uses. You can't really place a high-level industrial use with this method. And also it's partly because it's very hard to evaluate, because about 70% of non-domestic electricity demand is on half-hourly meters, and you can't actually get data on where that is demanded. You can get it from a citywide basis, but not on the level that we're modelling at, which is essentially building based, but we aggregate it to slightly higher spatial areas. So that's kind of in the SciSeds projects, that UCL's involvement in the stationary demand is mostly on the non-domestic side. The domestic energy demand is slightly easier because we have much better data from EST, who have a database called the Home Analytics database, which I believe is based on the heat data and the collection through that. And then they've got more detail about every single building. So that means within this modelling they can do quite a lot more detail, whereas with the non-domestic stuff we can only really look at bulk changes to energy intensities and floor areas, but with some division between uses. And obviously there's a lot of other data which goes into this modelling. I've described this in a little more detail, and I've got to look at later at air pollution stuff, but we have a lot of national and non-national statistics and data on population, etc. And we also have some input from other organisations, including AECOM and Fraser Nash, who give a bit more expert help on things like district heating and networks. I don't know, we haven't really mentioned that basically the modelling goes on at census areas within SciSeds, because that's how we can evaluate. So we aggregate up to these census areas so that, and try not to do too much bottom-up stuff because we don't know whether we're correct within that. But we're also doing grid-based modelling for the district heating in particular.
So we operate off people building archetypes databases, and essentially, this is a simplified illustrative database here. So for dwellings, we have detached, semi-detached, terrace, flats, offices and shops. And we'll have 3 efficiency packages, so it's low, medium, high. And for each efficiency package, we will have annual consumptions of space and other heat, electricity, air conditioning for each package, and peak demands, the capital costs of the efficiency package, and the network lengths required for each type of consumer, which we'll later use to work out the network costs. So we're doing scenarios heroically over 50 years, but of course the cities are really most interested in things while they still have a job. So we start off with drivers. The main drivers, of course, are the population of a city, but also the number of enterprises, premises, and of course in cities we need to get some handle on the non-residential population, i.e. the commuting tidal flow every day. So here's a scenario for our 3 efficiency packages, where gradually over time a high efficiency package is applied to a large fraction of the stock, but we still have remaining existing buildings which aren't refurbished. And from this we can then, for the stationary sector, work out the service demands in terajoules for transport, air conditioning and so forth for the different end users. We're also operating at a spatial level. So here's a scenario, and most of the data here is sort of illustrative for the West Midlands, which is about 2.4 million people. It includes Birmingham, which is one of our partner cities. And so here's an example here of calculating the heat load by kilometre grid square for that whole area. And obviously you tend to get an increasing density of the heat load as you go towards the centre. And here's a scenario for 2040 where this is gas heating, and you notice there's a big hole in the middle here of not very much gas heating, and that's because, as see in a minute, that's taken over, assumed to be taken over by district heating. So district heating, all these scenarios, by the way, they're not automatically optimised, but the users in the city will put in what-if scenarios. So here's a scenario for district heating, where this is the minimum heat load density at which you start putting in district heating. So as the minimum heat load density comes down, the number of consumers rises up. And here's the heat mix for the district heating, so that's the density again. And now we see in the early stages we're using a lot of combined heat and power. But as the national electricity system has more and more renewable electricity, We don't want CHP because it's more carbon intensive, and so we'll be using increasing amounts of heat pumps. And at the same time, we'll be putting in storage. And so here's the energy inputs and generation for this scenario. So we see the CHP rapidly increases, but then it reduces as our heat pumps take over in the longer term. So you can see what happens in the city, of course, is highly dependent on the national energy mix. Here's an example now of, actually perhaps this is better, looking at as the heat load density, minimum heat load density decreases. We start off with a very high heat load density in, say, 2025. And then as the heat load density decreases, our district heating expands. So this is 2035, 2045, and 2055. And you see that actually what happens as the heat load density goes down, that these schemes actually join up, going across the lower density areas. And this actually is reasonably realistic general picture of the evolution of district heating if one looks at how it's evolved in Denmark, for example. And then for each district heating scheme, the model calculates, I won't give you any time to read this, gives you the energy flows, the installed capacities, and the cost of delivered heat here. So this is for the whole city. This is for the largest scheme, where here we've got a heat delivery cost of 12 pence a kilowatt hour. As we go to the smaller schemes, we might go up to 20, 22 pence a kilowatt hour. And the reason for this is there are huge economies of scale. So a CHP plant of 10 kilowatts will cost 10 times as much per kilowatt as one of 100 megawatts. And this is one of the principal reasons why district heating can be economic, because of the economies of scale. And so here we look at the energy flows. So the positive ones are energy inputs to the district heating schemes, heat pumps and so on and so forth. And the only output here is the electricity generation by a CHP plant, which the revenue from that will be costed against the national electricity prices we saw earlier. You can see, and then here we have the economics of our district heating, and we see in terms of the capital cost, the network is a huge fraction of the total cost of storage, CHP, heat pumps and boilers. And this obviously is the big threshold for district heating, is how we get investment in this network, especially against the incumbent network of gas. But we can't use a lot of gas because of carbon limits. And here we have the annuitized costs of the system. And we see here, this is the value of the CHP electricity, and we see how critical that is in the overall economics of district heating. Then transport, we're looking really at two things. One is a change in mode, so a shift from car to non-mechanized bus and train, for example, in this passenger scenario. And we're also looking at the change in technology share. And basically we're looking at the shift to electricity. So electric trains, trams, cars, buses, and even now BMW make a 40-ton electric truck. So you can electrify the whole of transport, we think. And here are some sort of penetration curves. We're assuming that the electrification is saturated by 2050. And again, these are user inputs, these assumptions. When we work that through with our model, we can look at this is the energy delivered to the transport sector. We get a very large reduction because the end use efficiency of electricity is much greater than that of petrol or diesel. And then we also look at the emissions, and this is of particulates here, which is one of the two pollutants we're looking at in terms of health impacts. And you see this great big reduction because petrol and diesel here, the exhaust emissions are reducing to zero, but a large fraction of particulate emission actually comes from tyre and brake wear and road wear. So although you get this big reduction, you come down to this residue here, which is very difficult to do anything about. Then we can add up all the demands and supplies. So here is a deliveries scenario. So here we see gas and oil being phased out because you can't meet carbon targets if you use those to a large degree. And we see electricity and heat, district heat there replacing those fuels. When we look at electricity consumption, we have the space here, but now we're using a lot of electricity for transport and for our district heating heat pumps. That's electrification there. And here's our electricity generation from CHP, which tails off, and then increasing for solar PV as the major generation within the city. Then to look at how this thing actually works, we need to look at how it works in winter, spring, summer and autumn days here. And that's the heat profiles. Here's electricity demand profile. And we see the diurnal profile for heat and lighting and so forth, and leaving a trough, which is going to be filled mainly with electric vehicle batteries. In reality, of course, this will dynamically change this profile according to the availability of national electricity, renewable electricity. And here's our electricity generation, and you see we're dominated in the longer term by solar PV in the city. Don't expect a lot of other electricity generation in these scenarios. So the economics, which we're having a debate at the moment as to how to do this, but I think at the very least what we'll do is calculate the annual costs and revenues of energy-related services and technologies for consumers, suppliers and the whole city. We won't look at taxes, subsidies and market prices because these are somewhat arbitrary as opposed to the costs. Our inputs will be the national energy unit costs, as I showed you. And then we have technology, scale-dependent unit capital and operational costs of technologies. So we're taking into account a big CHP plant is lower cost per unit and more efficient and lower emission than a small CHP plant. And then we'll calculate the capital costs of installed technology, annuitise over the technology lifetimes with a discount rate, plus the annual operation and maintenance costs, plus the energy costs and revenues, to come up with a total annual cost for the city.
10 minutes.
Yeah. Okay. Okay. Just on the last section now. So air pollution calculation. This is what we're going to do. We'll collate base year concentrations by source for the city. We'll project city and national emissions. We'll project concentrations using these emissions changes, and then we calculate premature deaths and years of lost life with a health impact model.
So I think air pollution actually is one of the really interesting parts of this modelling, partly because there's really cool data, and partly because there's some sort of more mature modelling as part of it that we can add on to. So these are an example of one of the data sets that we use in the air pollution modelling, and it's NOx concentrations for each year in different cities under DEFRA's projections for 1 kilometre grid squares for the whole of GB, which paints a pretty interesting picture. So on the left-hand side is Birmingham and what's going to happen over time there. And the right-hand side, just for the audience rather than the modelling, is London. And something that I've been putting these online recently, and something that's really interesting and people have got hold of, is that basically around airports, nothing's going to change, even under these projections, which are actually, pretty good and fairly unrealistic. So, but using that data, we can put it straight into our model and start doing more interesting things with it, which Mark will go through on the algorithms. But the data is really interesting. There's one more slide. So as well as concentrations, there's also data on emissions. So there's a really good knowledge base of where emissions are coming from, or which sort of businesses and technologies, etc. And so there's really good spatial data, not temporal in this case, but we do know where these things are, which we can start to put into our modelling. This is again NOx. We're using NOx and PM2.5. Both the data sets dissect it by source as well. So there's from different types of roads and aviation, offshore, and slightly mysterious things like rural. What we found is that a lot of stuff is from outside of the city, a huge percentage.
I'll probably just skip to the chase now. Yeah, so we're assembling this data on air pollution concentrations. What you find is in most cities that it's quite dominated by what happens outside the cities, particularly in the southeast, where background concentrations are very high. So what we will try and do is use the city model to project emissions and then project concentrations, and then we will put this into a health model, and basically with the health model we calculate the premature deaths. So here you see the premature deaths from PM2.5, and here's the premature deaths from NOx, or NO2 I should say, and here's the combined effect of the two pollutants, which isn't just the sum of the two because there are synergies between the two. And another measure is the years of lost life, so you might lose 4 or 5 months of life on average, depending on the concentrations of pollutants. So I think that's our flyby. Thank you very much for listening.
Okay, we have some time for questions, about 20 minutes I think. That was quick. Could I ask you to stand up and just say who you are?
Yes, hi, my name is Verena Viskovic. I'm doing a PhD in energy economics at the statistics department. So I wanted to know a little bit more about your model and how do you implement it computationally, and what is the size of the problem that you're currently working with?
We are developing a model at UCL because we need to test the algorithms and so on, and the data sources. But the model algorithms are going to be programmed into a language called Mathematica. And this is the model which will actually be put online and commercialized. And then we will compare the results with what I call the toy model, as you've seen here, with the Mathematica model to check that there's no coding errors on either side. And it's pretty much all the algorithms are complete. We're just trying to finalize the air pollution algorithm, which is the most complex one.
So presumably your model is divided in like different modules, and then they pass each other data as they optimize within, or?
There's no optimizing. You just put in what if, and the basic flow of the model is somewhere here, there. So this is pretty much the flow. So we input a scenario for people and households, the fundamental drivers of energy services. Then we calculate stationary and transport, and that goes into our supply models. And then the whole lot goes into adding up the total costs in the city and the total emissions from all the gas boilers and the CHP and the traffic and so forth. And then that goes into our air pollution and health impacts calculation. I hesitate to say it because people think it's a toy, but actually this is programmed in Excel and Visual Basic.
Okay.
And it runs very, very, very quickly, actually. But they're all Turing machines, you know. So it's going to be put into Mathematica as well, and there's some stuff which Ed is adding in on GIS and so forth, which isn't so good in Visual Basic.
And what is your spatial representation of the city?
Well, there's two types really. There's irregular areas where we have lower level super output areas, medium level output areas, and citywide. And we have data at those different resolutions. As Ed mentioned, for example, half-hourly metering, the only public data is at the city level. Whereas there's a lot of domestic data for gas and electricity at the lower level super output area. So we have to kind of adjust things as we can. The district heating algorithm operates off a rectangular array of kilometre squares because the algorithms to join up into the heating schemes I showed you, it's just very difficult to do with irregular shapes.
Mike, and then I'll take you.
Hi, Mike Bell from UCL. Just quickly on the health issue which you came to right at the end, I just wondered whether you considered including other measures like quality adjusted life years as well as just premature deaths or nights in hospital or the sort of things which policymakers might make their ears pick up, you know?
Yeah, you know, there's so many different kinds of health impact of different, you know, affecting different segments of the population differently, and they have different chronic and acute impacts. And there's an awful lot of different ways of trying to estimate this. One common measure, of course, is economic value. So you can put values on hospital visits and death and so on and so forth. But the most commonly used measures, I think, are premature deaths, because that's obviously quite moving. And so if you see recently in the press, it's, you know, 40,000 people a year die in London because of air pollution. And so these are actually quite socially and politically, understandable measures. But of course, you can go right into a lot of detail and look at cancer and emphysema and you know, all these different things as they apply to children and adults and the old and the young and so forth. Yeah. It's quite difficult to do as it is.
Mike, are you happy with that, or do you want to come back at all?
No, the only thing I would say is I heard someone ask a question in a meeting the other day where they said, when you look for each death, behind that there's 10 hospital visits and 10 years of suffering or something like that, which I thought painted quite a striking picture of what was behind it. And I thought maybe it could be quite easily mapped on, but I completely understand it's going to be very complex to do that, so that's all.
Yeah, I mean, one difficulty, for example, is that you have the health impact of nitrogen dioxide, you know, the health impact of 2.5 micron particulate matter, and I know, well, you probably can't just add them together, so some say, well, we'll just multiply by 0.7. And then you've got pollutants like ozone as well on top of that. And actually, when you look at the epidemiological basis for these health impacts, of course it's done over very large areas with very poor information, and it's on a statistical basis. So. But yeah.
Can we take you?
Yeah.
And can you stand up?
Alessandro Rubino, editor at Nature Energy. I have a question about the way in which you model demand. Are you including any behavioral dimension on the demand side? So people are shifting the way in which they consume energy in the 25 plus year you're modeling. And so if there is any learning process and any role for storage, for instance, or any sort of energy efficiency measure, demand side management side. And the other thing is, you mentioned that these would be particularly relevant in countries like China, India. So how easy is to adapt this model to cities that are, I think, very different from like Birmingham or, I don't know, London?
Yeah.
Yeah, thanks.
The first question, we have discussed taking into account behavioural things like putting a sweater on, you know, or cycling rather than take a car. These effects are, you know, can be quite complex to figure out, and so we have thought of just having multipliers. Let's assume people would wear sweaters and you can reduce the temperature by a degree, for example. So we have discussed this, whether you have simple multipliers for that kind of thing, but at the city level we can't actually intricately model these behavioural changes in all the different kinds of buildings and types of households and so forth. The second question, and storage, unfortunately, to calculate storage and how it would operate, you have to do that at the national level, because how you operate your city storage depends on whether the wind is blowing in Scotland or somewhere else. So that's a rather separate issue, but we do assume that storage is built, particularly in district heating, because we think it will have a strategic role. Concerning other cities, I mean, basically it's a model, and if you can find the data for somewhere else, then you can do it. And certainly our aim is to commercialise this model and apply it to cities in the UK and then Europe, and hopefully, wherever we can sort of sell it, if you like.
Just one more thing on the first point is that, so the users of the model will have control over certain things within the efficiency packages, etc. So if they think that some sort of behaviour will happen and it will affect one of the things that they have control on, then they have the ability to move the model towards that and look at the way it's affected. And also the plan is to record how they change the model so that we're aware of what those users are leaning towards in terms of the scenario, so it's not just us saying we think this will happen.
So if I can take you.
Auburn Thurston from Energy. Question about land tenure, specifically related to district heat networks. I guess it's a qualitative thing, but is there any way, or is that a factor that you've looked at in propagation, installation of district heat networks? Is it a factor, and if so, is there any way of encapsulating it?
Well, one thing we're looking at is the user defines either maybe a minimal heat load density in which you're going to put district heating, but also you might say only public housing, for example. So you might by tenure make some splits like that, and there's also the take-up of district heating. But of course, the reality is when you go in and look in detail at an area, there's a whole level of detail which we can't accommodate, like the railways or canals or the natural rights of way for district heating networks, the existing heat networks, existing waste heat or low temperature heat supplies from rivers or lakes and so on. So there's a whole host of things that you would do if you're actually going to do an engineering design. And part of we're working with AECOM on district heating, Fraser Nash on electricity, we're working with Route Monkey on transport. So part of the idea of this is to do a first sort of screening for different options in a city. And then you say, okay, if you really want a district heating design, you have to go to AECOM and get a proper job done, taking all these accounts. So that's part of the idea, is to give hooks into people who would actually do designs and implementing.
Have any more questions? Yes, please.
I reserve from investor. Just wanted to understand, sorry, I can relate. So the output of the model is that for a given cost, you can identify that how much would be the reduction in emissions and what would be the beneficial health impacts. And if so, have you used a certain discount rate or a return on capital, and how does it sort of factor in?
Yeah. The users will put in what they want to look at. So they say, what would happen if we electrified transport? What would happen if we had district heating? And then the model will calculate the costs of that scenario, if you like, and what the air pollution emission will be, and what the health benefits will be, and the cost will be put on that. And at the moment, we're just discussing how to do the economics, but I think our starting point is we'll have a single discount rate applied to all sectors. Now we know that obviously a private district heating organisation will have a different discount rate from public housing. But at the moment we'll have a single discount rate so that you can, on a sort of level public policy level, compare the costs of one thing with another.
If I could just come in on that Mark, are you planning for your users, your user community, to be able to tweak that discount rate if users decide that they want to do that?
You can certainly put in a single universal discount rate and try it, but we've also been discussing, well, you actually want to look at the internal rate of returns over a particular district heating scheme, but to do that you would need cash flow for that particular scheme, so you can work out the net present value and then annualise the costs. But we can't trace the cash flows for the thousands and millions of investments that are going to be made in all these different things. So we're just discussing at the moment how we can elaborate so that, if we're going to do an installation program retrofit can we work out what the rate of return and the cash flow stream on that is?
Do you have any more questions?
Actually, maybe a follow-on.
Yes, please.
So with respect to district heating, this is something that government has been encouraging for a very long time, and economic returns are stellar, but still it's finding very difficult to get off the ground. All my since I've been involved in a couple, and it sort of doesn't really get off the ground in UK. And there must be some kind of a behavioral sort of barrier in there. I don't know if you've taken it into account, or you assume that for a given cost it automatically implements and people do buy into the new way of heating their homes and so on.
Within the model, we don't actually look at cost elasticity of policy, for example. But I mean, the short answer is to that one, I think, is that we have this incumbent natural gas network, which is probably most of it good for 40 years, doesn't need replacing. And but we can't use it a lot because we can't find low carbon gas efficient. And so things have to change. What's quite interesting is that we are getting details of network costing, and a very large fraction of the network cost is digging up the roads. And so when you look at the relative costs of electricity, gas and district heating, they're actually rather similar if you were to build them new. But the problem is we have this incumbent gas network. So, but somehow things have to change, and it's quite good through the Heat Network Development Unit of DEC. They're obviously doing surveys of a lot of parts of the country, but in the end, the energy market structure will have to change. So, for example, you'll have to be allowed to have a 10 or 15-year contract for heat with consumers, which currently is not generally possible.
Right. I can take a couple more questions, and then I think we'll bring this to a close. Do you have any more questions? Yes, go on.
So, since you said there is a huge economies of scale for the district heating, I think we could come up at the end with some highly regulated development, because I mean, you can't, if that is the case, it's meaningful that if the government or any local authority want to decide optimally how to implement this. But this doesn't really go hand in hand with the sort of gradual development of the district heating. Like you mentioned, it starts like with spots and then unifies. So I think the policy options behind this cost structure that you mentioned should somehow be taken into consideration, because they can change significantly the way in which the whole program is developed. So, I mean, it's not just a real question, it's just consideration, I think. But have you thought about it, or is it something that you would take into consideration at all?
Well, it's kind of, the problem is, as I say, we've got an incumbent gas network at the moment, and it's pretty low cost. And to heat the bricks up in the morning in the UK is 200 gigawatts of gas. Now the question is, can we replace that gas with all its carbon with electricity? With heat pumps and so on, we think we'll replace 200 gigawatts of gas heat with electricity. That's a lot of money. And so the question is, there's this threshold to get over. We have the current low-cost gas network and low-cost gas, and we've got to get over that into this low-carbon future. And this is the problem, how you adjust the market to do that. So, for example, in Scandinavia, you'll have things where it's mandatory to have district heating. And then you can go ahead. But we have a different sort of political economic culture here, and so it's a very difficult adjustment for the UK to make. But you can put it the other way around, saying if we don't make this adjustment, then personally I can't see how you can go to a very low carbon UK with high renewables without a lot of district heating, because of the multi-fueling option it gives you between CHP and heat pumps, and the very low-cost heat storage. Certainly, if you have individual electric heat pumps, for example, well, it's very difficult to fit them in small UK dwellings, and you won't have any storage in there of any size. So you can put it that way around. Well, what is your technical and economic solution to an 80 or 100% carbon emission reduction?
Colin.
Colin Calder, CEO of Passive Systems. Picking up on that same point, the benchmark everyone seems to talk about is district heating has got to be cheaper than a condensing gas boiler. So from a consumer perspective, we have to get to that price point. But as you said, in order to get to the right economies, you're going to have large investment in district heating systems. You're going to have large deployment. So my question is, do you put a cost on the health impact of, if we continued with our current model, which personally I think is completely unsustainable, but clearly is having a cost in terms of premature deaths and other health issues. Do you put a price on that in your model? Because we've got to get to the point where we're comparing apples and apples, which is you can't go on burning gas in homes and not take into account the cost of health issues and other impacts when you're looking at district heating, which is actually solving some of those issues.
Yeah. Again, we've had discussions about this, of putting a price of carbon on, for example, and that would radically change condensing gas boilers as opposed to heat pumps in district heating. And we could certainly put costs, values on premature deaths and value of lost life. You can certainly do that. We haven't got to that stage yet, including that in the economics, but there's no reason why not to. Yeah.
Could I make some observations about the approach that's been taken there and about the discussion that seems to be engendered? My understanding is that what we've got here is a tool for city decision makers to use to explore possible scenarios. And so the extent to which this models, as it were, from the bottom up, individual scenarios is actually quite limited. But if I, the city planner, actually have an idea of how I think I see my city developing, I can put that into your system, and it will show me the implications in terms of air quality and so on. Is that?
That's the idea, yes.
And it's interesting that the discussion that's taken place around the room has been to question SciSense in terms of its ability to generate bottom-up plausible futures for UK cities. And I don't think that's what it's for. Is that correct?
Well, what we aim to do is to, roughly speaking, get the technical energy flows and the investments and so on, as a calculator, right? And we will probably give some reference scenarios to the users, but the idea is that they will say, what if we insulate the city or put district heating in? But it also should be said that, there's an infinite number of ways it can be further developed, and that this is just the first stage. And what will happen is when the cities start using it later this year, doubtless other things will come up, and then we'll see how we can accommodate those going forwards.
I'm going to have to ask myself now whether I can have a supplementary question. Yes?
Yes, you can, Bob.
Thank you, that's very kind of you. How are you going to document the process by which the model is or is not taken up by the individual cities? Because it seems to me that is the really interesting question of what you've done here.
Yeah, part of what we're going to do is the actual data and model.
Yeah.
But we're also going to have parallel with that what we call a knowledge base.
Yeah.
Because there's obviously a lot of complex things here which many city stakeholders won't understand. In terms of documenting, what the users will do is they will put in their scenario assumptions, and this will be stored and accessible to us, so we can look at the sorts of things they're looking at. But also to say, of course, when you see this planning forum, no doubt in there will be these city stakeholders, but also EST people and so on facilitating this, and in order to get feedback and further development of it. be practicable for the stakeholders.
Thank you very much. Do we have one last question from the audience? In that case, I would like to thank our speakers for an excellent presentation in the usual way. I would also like to thank Len Williams, who has escaped, who organised, along with Mike Fell, organised the support for this event. So again, if we just give